So we have Eli visiting us this week from Colorado. And he's going to tell us about finding perfect superconducting circuits. Cool.
Yeah, exactly. So, yeah, thanks for the introduction. So, yeah, I'm going to be talking to you all today about some work that we've been doing on the automated discovery of new superconducting qubits. And as I hope you can tell from the title, let's see, is the mic? Okay. And as I hope you can all tell from the title, I want to try and have some fun with this talk and show how we can draw some inspiration from reality TV in our quest for new qubits. So, at their core, superconducting qubits are superconducting circuits, meaning that they're circuits made of linear capacitors, linear inductors, and Josephson junctions, which act as nonlinear inductors. And this is exciting in the sense that, at least in theory, any way we could arrange these elements into a valid circuit could be used as a qubit. But this is also intimidating because there's so many possible ways we could do this, and very few of them have ever really seriously been considered for use as a qubit. And even fewer have actually been built. And so this is where the bachelor inspiration came to be, because there's this sea of possibilities. I mean, so many possible options, and I want to make the good ones come to me. So with that, let us embark on our very own edition of the Qubit Bachelor. And I realize, it's superconducting qubits, so maybe the Tantalum Bachelor could have been a good title also. Now, I know that you all have here in Australia your own bachelor and bachelorette, but, I don't want to presume that everyone in this room watches, and so I'll give a brief primer for those of you who don't. The Bachelor or Bachelorette is a reality dating show where there's one bachelor or bachelorette front and center. Today, that's going to be me. And then there are, usually 20 or 30 strapping suitors. And today, that's going to be all of our possible qubit circuits. And in The Bachelor, over the course of, about 15 or so weeks of televised drama, the field is whittled down until they find, the suitor that's perfect for them. And usually it ends in a proposal. And in the case of the Qubit Bachelor, we're going to try and whittle this field down and hopefully find a couple circuits that, are worthy of bringing home and putting in our dilution refrigerators. So in summary, the goal of the Bachelor is to find love. And equally important, the goal of the Qubit Bachelor is to find the best superconducting qubits. Now, in running a show like this, there's really two main parts. The first is going to be casting our season. So that's defining our search space, figuring out, what are all the possible circuits that we can actually build from those elements that I mentioned before. Then part two is really going to be running our season of the show, trying to test compatibility and answer that question of, what makes a good qubit. But, just like dating in real life, there are many factors that go into making a qubit good. And it's up to the individual to figure out what's most important to them and to prioritize accordingly. And something to keep in mind as we're going through all this is that there's a lot that goes into, any of those axes that I write there. And there's more axes I didn't even draw. And so there's sort of infinite possibilities how we could go about this. And I'm not claiming to be modeling everything perfectly, but what we're trying to do is get good estimates and highlight some interesting examples within this really large search space. So why should you, care about any of this? So if you're an experimentalist, then you could think about the advancement from the Cooper pair box to the transmon, where we're able to really increase the performance of the system by increasing the size of the capacitor. And the point of this is to say that if we had real systematic ways for studying the performance of these circuits as a function of their circuit parameters or changing their topologies, then maybe we can make this leap faster for future systems. Now, if you're a theorist, and this is sort of an exciting talk for me because I think this is the first time I've given it to a room, I think of mostly theorists. If you're familiar with the XKCD cartoon Nerd Sniping, it has to do with a particular kind of brain that is very easily distracted or disabled by, if they're posed with a simple but interesting problem. And so this was very much me about a year and a half ago, where Josh and I were sitting there being like, okay, how many circuits can you make with this? And, fast forward to today, and I guess I'm talking to you all about it and making jokes about the Bachelor. So I guess it couldn't have gone too poorly. And, maybe a more serious justification here is that if, let's say you're studying a particular Hamiltonian and you're interested in finding a circuit that realizes it or maybe comes close to approximately realizing it, wouldn't it be great if instead of starting from scratch, you started off with a database of every circuit you could possibly build up to 5 nodes in size and what Hamiltonians those circuits realize. And so that's what our work is going to give. And sort of one little bonus thing here, because I know a lot of you think about error correction, is that one way people think about some of these more exotic superconducting circuits is as implementing an almost autonomous kind of error correction. So one example here is this dual mod circuit, which utilizes a more exotic quantum phase slip element that I'm not going to consider in my work to produce a circuit whose ground states are GKP code words. And so one way to think about this search over circuits is that we're trying to find circuits that, without using this fancy element, might also implement a similar kind of autonomous error correction. So before we get into our season of the Qubit Bachelor, I want to give a brief background on superconducting qubits to make sure we're all on the same page. So they are fully fabricated, engineered quantum systems that are made of circuits consisting of those linear capacitors, linear inductors, and Josephson junctions. And they are modeled in terms of this position-like flux variable and momentum-like charge variable. And it's the similar, familiar commutation relation as the XP we know and love. And there's a very strong analogy to considering these systems as particles with kinetic energies that depend on the charges that are constrained by potential energies that depend on the fluxes. And so hopefully these energy expressions should make sense in the case of the capacitor and inductor, because it matches, just classical circuits, the energy stored in a capacitor and inductor. And you can see how the Josephson junction acts as a nonlinear inductor if you do a power series expansion of that cosine. It matches the term for the linear inductor, up to second order. And so in general, if we want to add kinetic energy to our system, we put capacitors in our circuit. Potential energy to our system, we add inductors to our circuit. And the last thing here to note is that those constants out front in terms of the capacitance and inductance are often locked into this sort of EC and EL, to match this EJ over there. And so if you see this later in the talk, which you will, don't panic, it's just a constant. So the simplest possible superconducting circuit we could build, at least that does anything interesting, would be an LC circuit. And if we go through the full circuit quantization procedure, then we get a quantum harmonic oscillator with the energy levels we would expect that has a resonance frequency that goes with 1 over root LC. Again, what we would expect from classical circuits. And if we're trying to engineer our Hamiltonian here, then we have really 2 knobs that we can turn. The first would be varying the inductance or capacitance, which would change the effective mass or spring constant of our oscillator, thus changing the resonance frequency. But I think the more interesting knob we have to turn is actually changing the components in our circuit or the topology of our circuit to change the functional form of our Hamiltonian, instead of just changing, the coefficients out front of the operators. And so here we've gone to the transmon qubit, where we've swapped that linear inductor for a Josephson junction. And this is analogous to going from, a true harmonic oscillator to something like a pendulum, where it behaves like a harmonic oscillator, the small angle, but as you go higher and higher, you start to see the effect of the cosine potential versus the x squared. And it's this change that actually gives the transmon the anharmonic level structure that lets us, uniquely address the transitions and more easily use it as a qubit. So this is really going to be the focus of part 1, casting our season, is going to be what are all the different ways we can change the components, change the topologies, and what are all the resulting Hamiltonians that, we can produce. And, to be clear, this is a brute force solution, but it's a brute force solution that has had success, certainly in classical circuits. And so this is some recent work from, 2018, the most recently, where they're searching for new amplifier configurations by explicitly enumerating all the possible, 3 transistor circuits you could build. And they're able to successfully identify new circuits no one had ever considered that had properties that, in certain regimes were better than those anyone had previously considered. And the workflow here is you come up with all the possible options. In this case, it was 56,280, and you try and optimize some figure of merit over all of your possible configurations. And so we're hoping to replicate this kind of success when it comes to superconducting circuits. And it's worth noting that actually the numbers there are pretty similar to the number of superconducting circuits we're considering once you get to like 4 nodes. So without further ado, let's get going on our season of the Qubit Bachelor. So we're going to start off by figuring out what are all those possible circuits we can build. And the first step here is actually starting with unique topologies. So this would be all the different ways we can lay out our circuit, where the nodes of these graphs represent, or the vertices of these graphs represent circuit nodes, and each edge represents a place we put an element. And once we take a topology, we'll zoom in and actually substitute in on each of the edges. So in this case, we're going to substitute in either a capacitor, inductor, or junction onto this delta topology. And it's worth noting that in general, we allow for parallel connections, so you can have a capacitor and a junction on an edge. But to keep this example a little simpler, we're just doing a single element. And so here we have three spots to substitute, 3 options. So 3 to the 3, 27 possible configurations. And if anyone has some memories from March meeting, a funny story of this is I put up 3 cubed equals 27 on my slide. And I saw everyone pull out their iPads and take pictures of this 3 cubed equals 27. So I took that off because I don't think it's photo worthy. So I don't want to tempt you all. Yeah.
Oh, are we asking?
Yeah, of course.
Cool. So, do you, is there any reason to keep the circuits that don't have Josephson junctions in them?
Yeah, that is exactly what's coming next.
Okay, sorry.
So yeah, no, this is great. So exactly, I mean, they're not interesting for our use. And so literally, yeah, very next thing. So, there's other elements in this set too that we don't want. But, the idea here is we have these 27 configurations. Clearly, some of them are redundant, some of them aren't interesting. And so to focus our search, we want to try and reduce to a minimal sort of unique and interesting set. So that first step exactly is going to be to remove all the completely linear circuits, because we want non-linearities. That's the whole point of circuit QED, as Tom was saying before we started. Now, next, we're going to remove circuits that have series linear components. And this is because, we know we can actually combine these 2 inductors into one effective inductor. And that's going to make it equivalent to a circuit with 1 fewer node. Lastly, we actually want to go in and remove duplicates. So, in this case, all of these circuits that have 2 junctions and 1 capacitor are the same. I mean, just rotate your head if you don't believe me. And so we only want to keep 1 from this set.
So the type of triangle has no meaning. So whether it equilateral.
Exactly. I sort of regret that when I made this figure, I did not make an equilateral triangle, and I've been too lazy to go back and fix it.
The top right one is equilateral. So that's good enough.
Yeah. So, it's one of those things that every time I go over the talk, I think I should do, and I never quite get the motivation to do it.
I didn't mean to. The source.
No, that's okay. I think you're the first person to ever actually point it out. And so I appreciate it. It shows people here engaged. So, yeah, so in the end, we are left with only 4 circuits in our minimal unique set, starting from 27 initial configurations. And, hopefully you should be able to see that anything we're doing is going to be focused by this. I mean, if we're not considering redundant configurations, then we can really focus our efforts, searching across the variables that matter.
Can I ask
Yeah.
just a naive question?
Of course.
So when you get rid of 2 capacitors in parallel?
In series.
Sorry, in series, yes. But then, okay. And so you're allowed to just get rid of that island, no matter what the circuit is?
I guess unless you would want to couple to that specific board.
Okay.
And so that's sort of a subtlety we're losing there, but yes.
Are you considering, when you make inductive loops in this Hamiltonian, like, are you considering the effect of offset charges and external fluxes when you're choosing what to throw away and what to keep?
Not when we're choosing what to throw away and keep, but that is something we consider in optimizing the circuit performance. But I think in terms of this level of throwing away, it doesn't come into play at all because it's really, it's circuits that are equivalent up to basically moving around interchangeable components.
So while we're at it, so the top one there is 3 Josephson junctions in a loop.
Yes.
Is that materially different than 2 like on a squid?
I think it would be, yes. But I think it also, a lot of it'll depend on, how you choose to couple to the circuit.
Yeah.
So, let's see. Yeah, so. Trying to ask a question here now, which is that, hopefully these first 2 steps should be pretty straightforward. How we actually go about, removing the linear components and the series linear components. But, in this case here, we have a very symmetric configuration. And so it's pretty clear, when we're gonna get, equivalent circuits. But in general, we need a rigorous mathematical way to do this. And so we appeal to, everyone's favorite computationally hard problem, colored graph isomorphisms. And we use this kind of, it's a little bit counterintuitive, maybe graphical representation of a circuit called the component graph representation, where we actually map both circuit nodes and components to colored vertices, where those interchangeable components have the same color. So this would be a component graph representation of this, line here of a capacitor and a junction. And here would be the component graph of the flipped version. And we know that these 2 circuits are the same, just flip them upside down. And we do see in this component graph form that there is a straightforward isomorphism that exists between the 2 graphs. And so we would successfully identify this as equivalent. And in order to actually build up our minimal unique set, we do a whole bunch of pairwise comparisons. So we start with a set that doesn't have any circuits, and we build it up one by one, where we add a circuit to the set if it's not isomorphic to any other circuit within the set. And the color graph isomorphism problem, it's very difficult, but these graphs are small enough that we're at the, it still runs part of the exponential scaling. Yeah.
Are there examples of this, like, so it's detecting duplicates, right?
Yes.
Are there examples of when it's detecting a duplicate that isn't just like rotational symmetry of like the circuit, basically?
In this case, no, it's really just trying to do that.
Okay.
Is there a significance to the way you colored the nodes? So I notice
Yes.
2 node colors there.
Yeah, so this is a subtlety with the sort of component graph representation, which is that when you map, you're mapping the sort of nodes to different colors, but it's this identical components have the same color bit. So a node that only has 1 connection is treated as sort of a different element from a node that has 2 connections.
But it doesn't matter what they're connected to, it's just literally the coordination number of that node.
Exactly.
Yeah.
So to, go back to, it's been a little too long since a bachelor joke, so. Got to go back to it. So there's this joke around the Bachelor that they often cast very similar looking people into the same season. And, this is a mistake I want to avoid in the qubit Bachelor. I mean, it's, call me shallow, but what really matters to me is, the underlying functional form of a qubit's, Hamiltonian. And so to try and get at this question, we use some, we start off with these circuits that we've generated in that previous step. And we use some great existing software, SC qubits and SQ circuit, to perform the circuit quantization procedure and, give us a Hamiltonian that then we can use to try and answer this question. And going through this procedure, we've actually discovered that contestant 2 has some baggage that they didn't tell us about. And that baggage is parasitic capacitance on its Josephson junction. Yeah, and so, I mean, this is sort of it's a not so significant example, or not so profound. But really what it means here is that every time we model a Josephson junction, we really include a small parasitic capacitance in parallel. And so, yeah.
Even ignoring the parasitic capacitance, right? You'd get into trouble by analyzing the Hamiltonian of that thing because it's non-dynamical, right? It's purely like potential energy and no kinetic.
Exactly. And
Right.
so it's a necessity there. And so, yeah, to an extent, these two have, their Hamiltonians are very similar form, where, it has the same operators, although it's worth noting that they're going to live in very different parameter regimes, because the, capacitance of a dedicated capacitor is going to be much more than just the parasitic capacitance of a junction. And these different parameter regimes can have, large implications on the performance of the qubit. And so, an important point to make about this is that, in terms of these, similar looking men, our perception of their similarity, really depends on how they present themselves. So, it's their hairstyle, or they have glasses, facial hair. And so we actually got kind of lucky in this example, where they're wearing the same color shirt, similar level of facial hair, same style hair. And so we were able to really straightforwardly see that, they're almost the same person. And so the analogous point in our qubits is that the choice of coordinates matters a lot. And so this is sort of the simplest possible example where you can see this, which would be explicitly grounded transmon versus one that isn't. And they're the same circuit really, but at first glance, it doesn't seem how their Hamiltonians could be equivalent, because one depends on two variables, one depends on one. But of course, you can do a transformation of coordinates, where if you define sort of a sum and difference variable, you see that the dynamics of that ungrounded transmon only depends on the differences between the two nodes. It doesn't depend at all on the sum. And so you can recover this equivalence. And this question of what is the best choice of coordinates to analyze your circuit in, or to be able to see this equivalence with another circuit is, it's not such a straightforward question, and it's not one that we've solved. And so we have, some heuristics and some attempts we've made at trying to identify, good choices of coordinates. And, we've been able to identify a lot of circuits that can be brought into, the same form of a Hamiltonian, but, it's if we can't find it, we don't know that there isn't a choice of coordinates. And so that's why in this next table here, where I'm going to go over some of the numbers we found, there's a less than or equal to on that right-hand column. Because, these are the amount of the sort of number of groups we were able to form with, our choices of coordinates. But it might be that some of those groups can, be brought into accord with each other with some other, fancier second change of frame. So you do get a sort of exponential scaling that you would expect with the combinatorics, where, it really, I should probably factorial scaling, it really blows up, where, even at 4-node circuits, we're considering, 140,000 possible configurations. I mean, that's way more than, I don't know how many, grad students you have to sick on that to tell them to look at them all. But what we're excited about in our work is that, the reduction we get from this left-hand column to the right-hand column, where, we're going from 140,000 to, 11,000 to 500. And it's still, maybe above the numbers that, you could look at by hand, but it's going to really help focus any automated efforts, because, we're reducing the search space greatly. Yeah.
Can I just check I understand something?
Yeah,
I might
yeah.
have already said this. So for example, your 3-node circuit,
Yes.
with the exception of parasitic capacitance, like you're not considering, say, if I put a fluxonium in between each of those nodes, like you're not considering multiple circuit elements in parallel.
We are.
You are. This
Yes.
includes. Okay.
Yeah, this includes that. And so this is how we grow from, it was 4 here in the previous example. And so that's how we got to 88.
Yeah. Okay.
Yeah, so you could put a fluxonium, you could put a transmon, you could put a.
How does that
a
not just blow up? Like, surely I could just make I could put a fluxonium molecule and then I could make it longer and then.
Yeah, it's that you grow the number of nodes. And so if you have two nodes, you could put one fluxonium in between.
Oh, yeah, I see.
Yeah.
Yeah, okay.
Yeah.
Just a question, why is it less or equal to nothing?
It's less than or equal to, for the sort of subtlety I was trying to explain on the previous slide, which is that it's difficult to figure out what's the right coordinates to look at a circuit in. And so if you have two circuits and you're trying to answer the question of, can you make their Hamiltonians look similar? Then if you can come up with a, change of coordinates to make them look similar, then I know that I can make them look similar. But if I can't find one, maybe there's some way to prove that you can't, but we haven't done that yet. And so it's that, it might be you could find one, we just couldn't find it.
Do you know how how it's picking the variables that it's choosing for these Hamiltonians? Like, is this your unique Hamiltonians, is that obtained by you or is that obtained by SC qubits, for example?
It's a combination. So it's what we're trying is there's one which is the heuristics SC qubits uses,
Yeah.
which I guess my understanding is that they were made to sort of reproduce the 0 pi.
Yeah.
And so it has its ways of picking it. And then we've also done some attempts at sort of diagonalizing the capacitance matrix and trying to make two sort of Hamiltonians come into accord using that. But those are, one of them is cheap, but doesn't find it all the time. The other one is expensive, but finds more.
And so it's not trying to recast the Hamiltonian in terms of phase differences across JJs, for example.
Yeah, so how it works is it isolates all periodic modes. And so it says, okay, there might be certain periodic degrees of freedom in the circuit.
Yep.
And it isolates those. So it separates them from the extended degrees of
Right.
freedom.
Uh,
But then within the extended degrees of freedom, you have some choices. And if you have multiple periodic degrees of freedom, you also have some choices.
Yeah,
And
of
so
course.
there's once you get past that initial separation, then you have to
To make a choice at some point, yeah, for sure.
Yeah.
Cool, thanks.
So
I still don't understand so you allow between two nodes, you allow parallel
yes,
edges, I guess.
Yep.
But can't you just put as many as you want?
we limit at one per type.
Okay, okay.
And so for the linear ones, I guess it's combining elements and we don't consider squids as a result.
Hmm.
But, we sort of say, you could, if you wanted to, put it in after the fact.
Right.
So, some big numbers, because big numbers are fun.
Hmm.
And so five nodes is probably more than we can really analyze yet. But, we've been able to do the combinatorics, and so it's fun to include. I mean, we're at over 300 million possible configurations.
How long
even
did that
after the
take?
uniqueness.
How long did that
500,000.
take to obtain that thing?
Well, it's funny you ask, because it was a long time.
Perhaps unsurprising.
Yeah, so it was about, it was basically instantly to do the 2, a couple of seconds to do 3, couple minutes to do 4, and a month running 100 times parallel to do 5. And this is at the point where we're going up the bad scaling of colored graph isomorphism, and we're at a pretty bad, we're at an okay place here, but it's we're at about the limit. And
Because it's the second column to the third that's running graph isomorphism, right?
exactly, and so we're having to run,
Right, not
300
right.
million, but we're doing pairwise comparisons within that set.
Yeah,
So we're doing this squared number of, graph isomorphisms.
and then the next step, so the next step is also quite expensive because you're diagonalizing capacitance matrices or on subset of.
Yeah, and so it's interesting that the limiting step kind of changed where, in this step, this was the thing that took the longest,
Yeah,
and here, this is what took the longest. Yeah. And so, just, for even more fun, you know, what it looks like for 6 nodes. I mean, we're never doing that unless, you know, we want to make, you know, incredibly poor use of very expensive compute resources. So, let's zoom in a little bit now on maybe what this column on the right actually looks like. You know, it's this weird less than or equal to, and this is sort of a whole wall of math. And so resist the urge to zoom in too much on one of them, where these are, you know, all the Hamiltonians we were finding, but
You
I
did have that nerd, you had that.
nerd sniping.
Yes, once you got it up,
I nerd sniped the room. And so, you know, I've taken away all the coefficients here, just, you know, to make it actually fit on the page. And so these are just the operators. And the important thing to note here is that, you know, we have Hamiltonians and we've mapped them to particular circuits. And, you know, how many circuits in our 88 actually realize this Hamiltonian. And there, you know, the cool thing here is that there's probably already, you know, systems here that, you know, people haven't considered deeply yet. I mean, I don't know, maybe someone thinks everyone's considered each of these Hamiltonians, but you know, not to my knowledge. And so I think there's potentially some new qubits already here, you know, hiding in the 3-node circuits.
So these are the 3-node, these are the 22.
Exactly.
3-node circuits.
Yeah, sorry, I should
Yeah.
have said that.
What separates big Q from little q?
Yeah, this is the sleight of hand I try to pull. It's denoting a periodic from an extended. Yeah,
And so what corresponds to theta, what corresponds to phi?
so the little q var phi is periodic and the theta big Q is extended.
Okay, sweet.
And so with that,
Wait, sorry.
oh yeah, sorry.
Go back.
Yeah.
Second one? It's got, oh, phi squared, phi
Exactly.
second. I thought it was
Yeah.
Q. I see. Yeah, for sure.
To some extent, this ends up working out to be like, give you a transmon, give you a fluxonium, and there's only so many ways you can, you know, couple them together.
Yeah.
Or 2 fluxonium, or a transmon and a resonator, or
So what I feel like what's interesting about this, right, is that a lot of the ladder Hamiltonians are just the previous Hamiltonians coupled in certain ways, right?
yes,
So there's some weird nesting behavior going on here, right?
yeah.
Have you looked at that much?
So not really yet, no, but
Right.
we're sort of looking more at the 3-node circuits now and trying to, you know, identify good examples. So it's kind of what we're wrestling with now.
Cool.
Okay, good.
Yep.
Yeah, so we can move on to part 2 of our show now. And so on The Bachelor, they often talk about these kind of abstract checklists. There'll be, you know, 2 people sitting on a date, and one of them will, you know, they'll be like, man, you are like so perfect for me. Like you check literally all of my boxes, but no one ever tells you what those boxes actually are. And so, you know, I want to practice, you know, clear, transparent communication. And so I want to give you my good qubit checklist, you know, upfront. You don't have to work for it at all. So first of all, I absolutely have to have, you know, long coherence times. So that means if I start my system in a particular state and I don't do anything, it will just stay in that particular state. Next, I want high quality, fast gates. So if I want to transition my system from one state to another, I can do it with high fidelity and in a reasonable amount. Lastly, I would really love to have reliable readout. So if I ask my qubit, what state are you in? It's going to give me the right answer with a high probability. And again, hopefully in a reasonable amount of time. And really the focus of the rest of this talk is going to be on those first 2. The readout it's important, and you know, I thought it's worth mentioning, but it's, I think, pretty intimately tied in with experimental implementation. And so, you know, our high level theory approach, I don't think is so much to add there.
I have a question.
Yeah.
So after you have your Hamiltonians, how do
Yeah.
you decide which state's going to be your 0th and 1?
Yeah.
Isn't that up
yeah.
for debate?
Yeah, 100%. And so right now, we take the approach of essentially assuming it's going to be the ground state and first excited state. And it's something I'd love to look at is, you know, allowing more flexibility there. But, you know, it's the thing of there's so much to look through that we think there's a lot to gain even just from that. So the maybe easiest thing or most straightforward thing you could do to try and identify some, new circuits would be to try and find qubits or circuits that remind you a lot of those that people are already interested in. And so we're calling these copycat qubits. And maybe the bachelor analogy here is you're looking for people who remind you of your ex. And you're hoping that they're gonna have the stuff you liked about them, but maybe you're gonna, improve upon some of their shortcomings. And, like when people try and do this in the real world, we found that it's not quite that straightforward. And so this was, I guess one of our X's here, the 0 pi qubit, which is a protected qubit that people are interested in. And part of its, protected qualities are derived from, this Hamiltonian having small EC1 and big EC2. And so we were able to find 3 other circuits that reproduce the same functional form of the Hamiltonian, but they, lived in different regimes. Small and big EC1, we got every combination, except for the original. And so these circuits might be interesting in and of their own right, but they're probably not going to be interesting in the same way that 0 pi is. And our initial goal here was trying to find a circuit that reproduced some good qualities about 0 pi, but maybe was easier to build. Didn't include these crossing elements.
Sorry, I have a question about the middle one.
Yeah.
What are the modes that I want to think are analogous to Q1 and Q2?
Yeah, that's a good question. I believe for that one, it is the same 0 pi modes. And so it's the same combination of, the same variable transform that you do for 0 pi. But it's basically, you are uncrossing. I think it's easier to think of as you can sort of uncross the capacitors or uncross the inductors.
Yeah.
And so in the process, you kind of swap the light and heavy.
Oh, I see.
Yeah.
Can I ask a really
Of course.
naive experimentalist question?
Yeah.
So like, I look at all of them and I'm like, they're the same, because like, when I look at the 0 pi circuit, like
Yeah.
there's like really what that circuit is the capacitance of every single one of those modes to ground, and then there's capacitance between
Yeah.
every single one. So it's kind of just like which capacitances you've chosen to like eliminate
Yes.
or just ignore. But like we already kind of ignore most of the capacitances when we draw up the regular 0 pi qubit.
Mhm.
So like, okay. I
Yeah.
guess that's more of a statement. But is that the right intuition? Like, when I look like the 0 pi qubit, like that doesn't have the capacitance drawn in it that really you care about when you're
Yes.
thinking about the like heavy and light modes.
Yeah, so I think maybe the I think that's, totally accurate, true. And the thing maybe is that, my understanding at least is even, sort of experimentally, when you're doing the 0 pi, you're maybe trying to make these capacitances bigger than the ones we're not drawing.
Yeah.
And so in this case, we're trying to make these bigger.
Okay, so
And-
it's just which one is the big capacitor?
Exactly, and hopefully, any of these circuits you'd actually build would be, deviations from the ideal, and hopefully that, doesn't kill it.
What's the, oh no, they're both small, never mind. That's what I'm thinking about the top one. Right.
So wait, is the claim, so if I look at that top one, what is the claim about the similarity between the circuits?
It's that, you could write down the same sort of Hamiltonian, and I am hiding some stuff behind the scenes, so there's some small differences in terms of like how, how you couple to the zeta mode.
Sure.
And whether there even is a zeta mode. But, in the sort of ideal, every parameter the same case,
Yeah.
ignoring the zeta mode, you can write this down.
Yeah.
And the differences in the Hamiltonians will just be the magnitudes of the coefficients of EC1 and EC2.
Okay, yeah.
Yeah.
So in some sense, you're saying that even though you've matched Hamiltonians at the end and removed the same Hamiltonian, what you're saying is because everything comes along with some additional capacitance, like you are actually getting drawings that indicate different parameter regimes of ratios of capacitance kind of just there because these four pictures survive your collapsible types.
Exactly.
In some sense, they're very similar and they're capturing the fact that the physics of different regimes of EC would be very different.
Exactly. Yeah. And so maybe the goal here, which, I don't think we've entirely realized in our optimization yet, is that in some sense, we want to group these four together if we're trying to figure out what the best qubit would be. And we would say, okay, we're going to start off with this Hamiltonian, and we're going to say what possible regimes could we realize it in? And then from there, we can say which one of those regimes might be the best and try and focus on regimes that maybe there's a chance of actually building one in.
Yeah, because I suppose that was a question I had earlier on, which is that, I mean, for better or worse in the field, people tend to give different parameter regimes of the same circuit and Hamiltonian different names.
Yeah.
That's also, but if there is
It's true.
if there is a motivation for that, the qubit box physics and the transmon physics are materially different.
Yeah.
And it's kind of hard, there's something parameter search that one would have to do to identify that in these more complex circuits.
Yes. Exactly. And, it's sort of, especially when you're in these more complicated circuits, you might have these, coefficients that they don't depend so straightforwardly on Cooper pair box and transmon. You have one capacitor to change. I mean, obviously there's sort of the parasitics, but you can get to a lot of different places in this regime by tuning one parameter. But here it's, the change of coordinates makes it actually impossible to, switch from having a small and big. It's a function of, one of them is, has a, 1 over EJ or, the capacitance of a junction. And, one's over the capacitance, the sum of the capacitances of the actual capacitors. And so, you have to think more, or more hard. Have to think harder about bigger circuits.
Is that middle one saying that I want big EC for the junctions or for the capacitors?
It's not saying, I guess, that it's assuming, so it's assuming parasitic capacitance on the junction.
Sure.
And, normal capacitance on the capacitors. And so it basically just flips the coefficients on the modes. And so it by uncrossing the capacitor or the inductor, you basically swap the coefficients in terms of the extended mode.
But I still want to imagine when I see capacitor that has a big capacitance.
Yes, exactly.
Cool.
Exactly.
Cool.
Yeah.
That's super strange because this is just two non-linearly coupled LC oscillators.
Yeah.
Strange.
Yeah, you can do a lot with the change of coordinates.
Cool.
Yeah.
Cool.
So, I talked about the 0 pi as this protected qubit. And so, I want to talk a little bit more about what that means and, what constitutes a protected qubit. And I guess if anyone's gone to a protected qubit session, like at March meeting or something, this, figures on the bingo card. And so, to be a protected qubit, you have to be protected against the, two, main types of noise we worry about, which would be decay and dephasing. And so to be protected against decay, the ideal situation is you want your system to have, approximately degenerate ground states that are separated by a potential energy barrier, which the idea here is to make it very unlikely to, accidentally decay from one of your computational states to the other. And you can think about it from a Fermi's golden rule perspective, which is that, whatever operator you expect to be your decay channel, you want the matrix element between your computational states of that, operator to be exponentially small, ideally in the barrier height, or something that you can tune to, make that decay chance, go down as low as you can. And now to be protected against dephasing, it's a little bit more subtle of a point, where to explore it, let's go back to this Cooper pair box and transmon example from before, where if you're trying to make, a qubit, a quantum computer, you need to introduce control knobs so that you can do gates. And when you introduce a control knob, you necessarily introduce noise into that control signal. And so if your system has an energy spectrum that, is very dependent on that external parameter, which in the case of the Cooper paradox, it is, then as you have random fluctuations in your control signal, you're going to get random fluctuations in the energy splitting of your qubit also. And that's bad for your system. If you just think back to second semester quantum mechanics, you use time independent Schrodinger equation and see that if your system is just idling, then you're going to pick up a relative phase between your computational states that depends on that energy splitting. And so if you have random fluctuations in the energy splitting, you're going to start to accumulate random phases that you're not going to be able to correct for after the fact. And so this was the big, one of the big innovations of the transmon was flattening this dependence on the external control parameter. And so, mathematically here, we want an exponentially small dependence of that energy or the range of that energy splitting on the range of your control parameter. Now, something to keep in mind as we're talking about all of these circuits and trying to optimize them is that it gets very difficult as you're trying to optimize bigger and bigger circuits. We sort of get hit twice by the curse of dimensionality. So first of all, these small circuits just have way fewer parameters we're trying to optimize over. In the case of fluxonium or transmon, we only have 3 parameters to optimize over. I guess, we can go to 4 if, you include a capacitor on fluxonium. But that's still not very many. Whereas if you're going to a circuit like 0 pi, we've gone from a 3 or 4D optimization problem to a 9-dimensional optimization problem. And you combine that with the fact that the underlying circuit model also grows exponentially with the number of nodes in your circuit. And it's also, this highly nonlinear landscape you're trying to optimize over. And it becomes, difficult pretty fast.
Why do you have 2 NGs for the 0 pi?
I guess it's that, in theory, at least, you could drive the, theta or phi mode.
But shouldn't phi be like fluxonium and be invariant under NG?
Well, my understanding is if you like how in Androsh's realization, he coupled essentially those 2 of the nodes, and it gave some mixed theta phi kind of coupling, where it was mostly phi, but a little bit theta. And
Cool.
so, yeah. So nonetheless, it's difficult, but for these smaller circuits, you can still kind of take a brute force approach here. And so this is sort of a proof of concept we were doing, where we're trying to optimize the performance of a transmon, to give us confidence as we're moving forward to some of these more complicated circuits. And so here, we're actually trying to directly estimate, the number of gates that our system could perform. So that would involve both an estimate of the coherence time and of how long we would expect, say, an X gate to take. And, we're not so concerned here with where we say the absolute best place to operate your system would be, because, these are estimates at the end of the day. But we think that, the region we say is good should be meaningful. And we were encouraged by the fact that, major industry players are operating their transmons, within this region that we say should be good. And also that, we're correctly picking out the Cooper pair box regime up there at the top left with sort of the small capacitor. And I guess, we're saying it's 4 orders of magnitude worse. And actually we might be underestimating that difference. But, we're saying it's much, much worse. Yeah. Who wants to go first?
Andrew.
So suppose this gets to me, so in assessing what the gate time is, you're sort of assuming that you're coupling, you're assuming something about a gate. I presume you're saying this in a symmetry field you're applying.
Yep.
That could be biasing you in some ways. Like if I took the 0 pi qubit and imagine being able to get a really large capacitive ratio, I would just turn off all the matrix elements that would allow that to happen. And so some of the protected gates might need, protected qubits might need gates that are just not facilitating signals. I'm just wondering, is that, I suppose, is that kind of a limitation that here this is, you're envisaging a particular approach to doing a gate.
Yes, 100%. And so, at least in this case, what we're considering is really a, direct drive, one state to the other with a Gaussian pulse and
And they're the lowest two states and so on and so forth.
exactly.
Not even like some run and carry on. Or
Yeah, and that's really sort of a next step we're considering where, our first step is, I don't think we would discover zero pi with our initial approach here, but the goal is trying to see if we can discover some good three-node circuits that have, a balance of straightforward control with reasonable coherence.
Right.
And so what I sort of envision as the next step is exactly including those kind of Raman transitions where we also are able to more explicitly think about how we would couple to the circuit. And that's something that I think in terms of the automated analysis isn't quite there yet, but I want to include that next, which is, trying to identify, hey, you might have two really well-protected states that might not even be the first two states, like in 0 pi, 0 and 2. But then, they're both strongly coupled to some higher level state. And so being able to identify that is definitely a goal for the next version. Yeah.
Can I just maybe
Of course.
explicitly ask how are you calculating that? Like, are you taking into account the unharmonicity and the matrix elements between, like, what goes into that calculation?
Are you talking about the gate time or the coherence time?
The gate time.
So for the gate time, yeah, so it's considering the unharmonicity.
Okay.
Right now, it's not considering the matrix element explicitly.
Yeah.
I think that's also something that we're sort of on the fence of whether we want to try and include
Yeah.
more explicitly in this version or the next, but I think we can get into hot water with some of the bigger circuits. And so right now it's really assuming that it's same order of magnitude matrix elements, and then we kind of cap essentially a max power.
Yeah.
And then, we've analytically solved for what would be the, population transfer under a Gaussian pulse.
Right.
And say, what would be the sort of right balance of if you consider sort of a decay only and say, okay, you've decayed over the course of your gate, and how long would be the right gate time to sort of balance leakage versus decay.
Okay. So like, if I'm just like wildly imagining some circuit where potentially like you might have minimal unharmonicity, but you're somehow protected by symmetry or something from like,
Yeah.
it doesn't capture that type of.
Not right now. And again, yeah, it's definitely something that I want to include, but I guess the hope is that even without including that, there's so much that hasn't been considered that we'll be able to identify some interesting stuff.
Yeah.
Yeah.
So when it comes down to the lowest energy levels, I imagine many of the Hamiltonian would actually be more or less similar. So terms in the Hamiltonian, which only affect the order. So have you ever considered that in this?
Sorry, say one more time?
So if you only care about the lowest energy level.
Yeah.
Many of the Hamiltonians will be more or less similar, approximately, because there are terms that only affect the higher energy.
Yes.
Have you taken that into account? Maybe that will simplify some of the optimization.
Yeah, no, but that hasn't been something we've really taken into account. I think in our analysis so far, it's really been focusing on the lowest lying states. Right. So this is sort of where we're at right now, where we are trying to optimize over this set of 3-node circuits. And so we're explicitly considering all 88 of those circuits that we had showed on that table. And it's big enough where we can't do the brute force approach we did for the transmon anymore. And so to try and optimize this estimate of the number of gates, we turn to, I guess, we're doing a kind of dumb enumeration. We're not trying to be so clever. And so, we're using basically a 0th order optimization, a genetic algorithm where we are, hoping that this will give us, a decent optimization in this system that we know very little about. And so far it has been doing a good job. And the goal is giving us a ranking where the exact numbers, again, we're putting out aren't so important, but the relative position of the circuits on this list, we think is real. And so the goal is to highlight some interesting performers at the top, which then we're going to look at more closely. And one of the goals here is also to try and produce circuits that, that might again have a chance of being implemented experimentally. And so, I imagine if I said, hey, I have this awesome new circuit idea, but there's 7 circuit parameters that you're gonna have to hit to within 0.1% tolerance, and I haven't even considered, the parasitic all-to-all kind of couplings yet, then I imagine I'd get kind of laughed out of the room. And so we, want to do a stability analysis, as we're calling it, where we want to say that any circuit we're highlighting is good, maybe has a tolerance of, plus or minus 10% on either side of any fabrication parameter, where maybe it knocks down the performance estimate by like 30%, but it doesn't knock it down by a factor of like 1,000 or 100.
Is there any rule as a lazy experimentalist?
Yeah.
Is there any rule that like I can say, like if I'm thinking about a fluxonium or a transmon, right, or even a qubit pair box, then like for my flux, for my external flux and external charge variables, like anything interesting is going to happen at 0 or half. Can I like reduce the dimensionality of these problems just a little bit by saying, I'm seeing N gate with some like big numbers there. I don't know what they are, but like, can I say I'm only going to consider 0 and half for all of those and call it a day, or maybe a quarter? For quasi-particles. Yeah.
Yeah, no, exactly. That's been the approach we've taken so far as a way to try and simplify it.
And that, is there a reason for that? Like, can I justify that? If like I can for a 2-node circuit, but like, does the intuition and the justification for that extend to higher order circuits?
Yeah, that's been something we've been trying to figure out. And I guess we haven't come up with a, maybe concrete reason why yet, but it's sort of what we've been running with, and something we were talking about like right before I left on this trip. Yeah.
When you say differential evolution, do you mean gradient descent?
No,
Or what are you doing with that?
yeah, so it's an evolutionary algorithm. So it is a not gradient descent in the sense of no gradients involved. It's just uses the objective function we're trying to optimize, and it's an algorithm that broadly speaking takes some kind of random or structured sample and sort of evolves a population where it tries and sort of mutates the best performers and say, okay, like evolution, where we're trying to sort of select for better performance of a population. And so it's no gradients involved.
So in a sense, you start from some point in the big parameter space.
Yeah.
And you look at different directions.
I-
Best.
We start off with maybe 100 or 1,000,
Right.
random spots. And then there's rules on how to move each of those spots.
Like
And
particle swap. Is that what you mean?
it's like a particle. So I mean, sort of similar concepts.
What's the objective function?
It's this, number of gates. And so it's the same thing that I was, plotting explicitly
Yeah.
over here.
Is there an easy way to sort of search for, like, have a function that's like, that finds something that looks like, a grid state or something with like an approximate grid state with sufficient good approximation?
Yeah. So that's something we've been considering, is trying to instead target like specific looking states. And so, we hadn't thought about, maybe the grid state in particular, but like trying to find very disjoint states, or sort of ones that are insensitive to the external control parameters. But it's sort of a choice of, you can target something more specific, or you can, trust that the metric you're making is going to capture, sort of good systems in it. And, we sort of took the latter approach for now.
Sorry.
Yeah, no.
How do you, so like, these experiments where you can show that like flux noise, for example, scales with the perimeter of, your loop and things like, I'm curious as to like how you make decisions about what, like, there's got to be some like details about the noise in these calculations. Like, are you assuming that like the best case noise scenario for a fluxonium will apply to some multi-loop huge circuit Like, how do you make those decisions when you're predicting the number of gates in bigger circuits?
Yeah, so I guess we're sort of assuming uncorrelated noise within the circuit. And I mean, under the hood, we're using, SQ circuit as a way to, calculate it for arbitrary circuits. And so, we're inheriting all of their assumptions there.
Yeah.
And so at the end of the day, it is definitely a rough estimate. But I guess our approach has been, until, people start building, these really big circuits and we get, more feedback loop on the noise, then, we're probably not going to be able to do much better than the estimates. Maybe the more assumptions we make, the more liable we are to make bad assumptions.
Just a little bit mindful of the time. The Spanish Inquisition has slowed you down.
Yeah, no, this has been great.
Maybe if there's a way that, I'm sure there are some of us that are really interested in continuing with these details, but maybe if
Yeah.
you could, maybe just like a summary and we
Sure.
can let the.
I think we're pretty much at the end, actually.
Yeah,
So
okay,
We've-
cool, okay.
We've, yeah, I said more theory here. Can't automate everything. So I guess to sort of wrap it up, just want to talk a little bit of where we're going. And so, the goal here is really to identify some new candidate qubits that are interesting. We have no claim that we're going to find every interesting qubit in this set, but it's a sufficiently unexplored space that, we think we're going to be able to get some interesting candidates, even from our, sort of simpler methods. And, the enumeration approach we're taking ensures us that at least we're considering all of the possibilities. And, maybe at a high level here, we're excited that we're considering basically all possible small circuits that someone could build. And even in classical circuits, they don't really think about the bulk performance or the bulk properties of, a 15 node circuit. This is a, diagram that I just screenshotted from Wikipedia on, an op-amp, where they're not considering the performance of this whole big circuit. They're looking at these smaller modules and how they connect together. And so our enumeration is going to provide all of these small modules for these superconducting circuits, whenever these larger ones, start to be built. And so, lastly, got to advertise, I guess we're going to put out the, software we're using to do this enumeration, and put a paper out the end of the summer is where we're targeting. So with that, we have reached the end of the qubit bachelor.
Awesome, thanks very much, Eli. I suppose I'll assume that, okay, first, does anyone want to ask a question? Yeah.
One last one.
Yeah.
You went from 4 nodes to 5. Did you
Yeah.
exclude non-planar circuits?
We did not.
Because once you have a graph with 5 vertices, you can have non-planarity.
Exactly.
So in terms of actually experimentally like fabricatable, that might be not optimal.
Yeah, I totally agree. And I think the theorist answer is, I guess it might be interesting. I think the practical answer is we're probably not even going to optimize up to 5 nodes. So, we'll put them there for completeness, but I think there's so much left to do in 3 and 4 nodes that I don't think it's worth spending too much time worrying about, non-planar kind of circuits. And I guess I think people at MIT also for their 0 pi's are starting to try and build some of these crossing capacitors that kind of use 3D. So maybe,
Yeah.
Yeah. maybe it's in the future.
Yeah, thanks, Eli.
Yeah.